Hello everyone. In this video, I am going to explain how I designed this ACS723 current sensor module and how we can use it for current measurement. In the previous video, we understood how to read analog voltage using ADC. Now, we will use the same ADC concept to measure current. In power electronics and electric drive applications, current measurement is very important. We need current feedback for protection, monitoring, and closed-loop control. But a controller cannot read current directly. So, first, we need to convert current into a voltage signal. This is where the current sensor is used. In this setup, I am using a single-phase transformer connected to an R load. The load current is passing through this path, and I want to sense this current using the ACS723 current sensor module. For comparison, I have also connected a current probe and an analog ammeter in the same setup. The current probe helps us observe the current waveform, and the analog ammeter gives a direct current reading. Now, our aim is to use the ACS723 sensor to convert this load current into a voltage signal. After that, this voltage signal can be read by a controller through the ADC. For this module, I am using the ACS723 Hall-effect current sensor. This sensor measures the current flowing through its input path and gives an analog voltage at the output. Since the output is a voltage signal, we can connect it to the ADC pin of a controller. The ACS723 works based on the Hall-effect principle. When current flows through the sensor conductor, it produces a magnetic field. The internal Hall sensor detects this magnetic field and converts it into an output voltage. So, the output voltage changes according to the input current. In this current sensor module, I am using a 5 ampere bidirectional ACS723 current sensor. When there is no current, the sensor output stays around 2.5 volts. Now, as the input current amplitude increases, the output voltage also changes more clearly. Here, one important point is that the output waveform is not centered around 0. It is shifted around 2.5 volts. Because of this offset, the complete AC current waveform is converted into a positive voltage signal within the 0 to 5 volt range. So, the ACS723 output voltage can go up to 5 volts. But here, I want to read this signal using the F28379D LaunchPad. The problem is that the ADC input of the F28379D LaunchPad cannot accept the full 5 volt signal directly. Its ADC input range is limited to around 0 to 3 volts. So, before connecting the current sensor output to the ADC, we must reduce the voltage level. For this purpose, I have used this signal conditioning circuit. First, this 10 kilo ohm resistor and this 20 kilo ohm resistor form a potential divider circuit. This potential divider scales down the output voltage coming from the ACS723 current sensor. So, the sensor signal is brought closer to the safe input range of the F28379D LaunchPad ADC. After that, the signal passes through these resistor and capacitor sections. These sections work like a simple filtering stage. They help to smooth the waveform and reduce unwanted noise in the signal. Finally, at this output point, we get a properly conditioned voltage signal. This signal can now be safely given to the ADC for current measurement. Now, let us quickly look at the terminals of this current sensor module. This board is designed for measuring 5-phase currents. At the top side, we have the current input and output terminals for all 5 phases. At the bottom side, one set of output signals is provided for connecting to the ADC pins of the controller. Another set of output points is provided for observing the sensor waveforms directly on the DSO. This is very useful while testing and debugging the module. At the bottom right side, these 2 banana terminals are used to give a single-phase AC supply to the board. From this supply, the required VCC is generated for powering the ACS723 sensor boards. So this module is not only a current sensor, it is a complete 5-phase current sensing interface with controller outputs, DSO testing points, and onboard power supply. To make this current sensor useful for most of the motors available in our lab, I selected a 30 ampere measurement range. For this range, one option is to directly use a 40 ampere bidirectional ACS723 current sensor. But here, I followed a different approach. I used a 30 ampere by 5 ampere current transformer along with a 5 ampere bidirectional ACS723 current sensor. The current transformer first steps down the motor current. So when 30 amperes flows on the primary side, we get 5 amperes on the secondary side. This 5 ampere current is then given to the ACS723 current sensor. In this way, by combining a 30 by 5 ampere current transformer with a 5 ampere ACS723 current sensor, we can design a low-cost 30 ampere current sensing module. This module can be easily interfaced with low-cost controllers like the F28379D LaunchPad, Arduino Duo, and ESP32. Now, let us observe the relation between the input current and the output voltage. Here, the input current waveform is centered around 0, but the output voltage waveform is centered around a fixed voltage level. This fixed center level represents the zero current condition. Now, notice this important point. When there is no current, the output is not 0 volts. It stays at about 1.5 volts. This is called the zero current offset voltage. So, while calculating the actual current, this offset voltage must be taken into account. To reconstruct the actual current, the first step is to remove the zero current offset voltage. Once this offset is removed, the waveform becomes centered around 0. The next step is scaling. Here, the offset removed voltage signal is converted into actual current. For this, we multiply the voltage signal with the proper scaling factor. In this way, the measured sensor voltage is reconstructed as the actual current waveform. Now, let us see the physical connections of the sensor module. Here, I am using the Y channel for current sensing. The load current enters through Y in and leaves through Y out. Now, the 65th pin of the F28379D LaunchPad is connected to the Y channel output from the first output port. Through this connection, the LaunchPad reads the Y channel sensor output using the ADC. The same Y channel output from the second output port is connected to the DSO. This allows us to directly observe the sensor voltage output waveform on the DSO. The current probe is also connected to the same DSO. In this way, we can compare the actual current waveform with the sensor output waveform. Finally, a single-phase AC supply is given to the sensor module. From this supply, the required VCC is generated for powering the ACS723 current sensor boards. Now, the load current is kept at 0. On the DSO, we can see the zero current offset voltage as 1.6 volts. The same voltage is also coming through the ADC in Simulink. So, I will subtract this offset voltage from the ADC output. After this subtraction, the current signal becomes centered around 0. Now, I will apply a load current of around 3 amperes. This value can be observed either from the analog ammeter or from the current probe waveform on the DSO. Here, channel 1 represents the current sensor output voltage waveform, and channel 3 represents the current probe output waveform. Using the signal statistics option in the Simulink scope, we can see the RMS value of the ADC output voltage after subtracting the zero current offset. Here, the offset removed voltage is around 63.5 millivolts. By comparing this value with the actual 3 ampere current, we can calculate the scaling factor. Now, I will add this scaling factor as a gain block in Simulink. After this gain block, I will add a low-pass filter to get a smooth current waveform. Now we can see the same 3 ampere current on the scope. This means we have successfully sensed the actual current. Now, I will verify the sensor output at different load currents. First, I will test around 5 amperes. Here, we can observe the current value on the ammeter, the waveforms on the DSO, and the reconstructed current in the Simulink scope. Then, I will increase the load current to around 8 amperes. Again, we can compare all 3 readings on the screen. If the ammeter reading, DSO current probe value, and Simulink RMS value are nearly matching, then the sensor calibration is correct. So in this video, we designed and tested an ACS723 base current sensor module. We connected the current sensor output to the F28379D LaunchPad, removed the zero current offset, and applied the scaling factor in Simulink. Finally, we verified the reconstructed current using the ammeter, DSO, and Simulink scope. I hope this video helped you understand how sensor voltage can be converted into actual current. Thank you for watching.